Hi class. We're switching gears a little bit here. Then in this next section, we're going to talk about vectors, and this section is pretty big. So I'm actually going to split this apart in half into two parts. So there's 6 learning objectives. So we're going to cover the first 3 learning objectives in this video, and then I'll make a separate video for the part B, the second half. So the very first part is a lot of terms. So objective 1 is interpret vectors geometrically, right? So I put here, right, that here are some terms that are important for this section. So the first thing to talk about is, in physics, the mathematical quantities that are used to describe the motion of an object can be divided into 2 quantities. So we call these scalars and vectors. So scalars are quantities that are described by a single value called the magnitude, which is the size or measurement of the quantity, right? But then vectors are quantities that are described by both magnitude and direction, right? So vectors have both magnitude and direction. So it's important to denote that, right? So we have to have both of these properties in order to have a vector. So then the speed of an object is a scalar quantity that tells us how fast an object travels, right? And by contrast, the velocity of an object is a vector quantity because it tells us how fast the object travels and which direction, right? So there's some difference in terminology there, right? So then a vector in a plane is a line segment with a specific direction. And we denote a vector, we can denote it by writing PQ and drawing an arrow above it. And P is called the initial point of the vector, and Q is called the terminal point of the vector. So you can see, like here in the diagram, I have that labeled. Notice the arrow, right, the vector goes from P to Q, right? So we always write the starting point or the initial point first, and then we write the terminal point next, right, second. All right, so that's important to denote. So initial points where you start and the terminal points where you end, right, to show that length. And then the length of the vector of the line segment, we call that the magnitude, right? So you can see that here. And we denote this by putting, it's kind of like double absolute value, if you will, right? You put it in these double bars, right, like shown here. And again, that's the length of the line segment, right, how long that is. So we can use the distance formula between those 2 points to figure that out. And then using I wonder if I might have that word doesn't make sense. I wonder I might have a typo here. Let me check that out really quick. A lot of this I just pulled directly from the text, trying to pull what I thought was the most important parts. So let me see. Yeah, I thought so. That should be context. So you could fix that in your notes. This should be context. So using the context of the displacement of an object, the vector PQ refers to the object's overall change in position from moving from point P to point Q, right? So I have this diagram here, right? So just to reiterate, right? Basically, if we have a point P and we have a point Q, and I draw this line segment with an arrow showing the direction, then that's what we consider a vector, right? And the length of the vector is magnitude of the vector of PQ, right? So that's vector PQ. So that's all that's showing. And then 2 vectors are equal if they have the same magnitude and the same direction, right? So the vectors don't have to be on top of each other in order to be equal in that sense. We just need them to have the same length, right? The same magnitude, and also the same direction, right? So another way that we can denote vectors is by using boldface lowercase letters. So you can see like little u, little v, and little w all boldface. So that's just another way that we can show vectors. But that's actually quite hard to do when you're writing things out. So like instead of writing like for example u, I could write this as u with a like vector symbol above, right, and like a array, or some people will just draw a bar above to signify a vector, right? So these are all equivalent ways to show vector u, for example. Right. So I just wanted to make a note here. I think I said this all out loud, but all of these vectors are equal to vector AB. Right? So all these vectors in this diagram are equivalent to vector AB. They all have the same magnitude, and they all have the same direction. Right? All right, so here we have example 1. So we have vector v extends from 0, 0 to 3, 4, right? So this is the initial point. And this is the terminal point. Right, as described before. And actually, this vector v is special. We call that a vector in standard position, right? So a vector in standard position has its initial point at the origin. Right, so v is in standard position. So we want to find the magnitude of this vector. And it's not really necessary, but just to help us visualize this, let me draw this for us. Right, so vector v starts at the origin and ends at the point 3, 4. Right, so let me just line this up. Right. Right. So that is vector v. And what we're after is what's the length of that line segment. So essentially what we want to do is use the distance formula, right? I want to find the distance between this point and this point, right? So remember, the distance formula is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Right, we're essentially using the hypothesis, Pythagorean theorem, right, to find the hypotenuse, the distance of the hypotenuse. Right, and let me go ahead and draw while I have this here. Draw w, right? So vector w, the initial point's at -2, +3. Right, so it starts here. and then it goes to -5, -1, which is here. All right, so just try to line this up the best I can. It would be going in this direction. Right, so that's W. Right, so there's W and there's V drawn. So what we were asked to do is find the magnitude of each of these, right? So the magnitude of V is going to be equal to the square root of, right? So we want to take, remember, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Let me just get rid of that ruler. So this would be equivalent to the square root of -5 minus -2 quantity squared plus, whoops, hang on, I was looking at the wrong vector. I was looking right above. That's for W, sorry about that. So this would be 3 minus 0 quantity squared plus 4 minus 0 quantity squared. So this would be equal to the square root of 3 squared, which is 9, plus 4 squared, which is 16, which equals the square root of 25, which is 5. Right? So then the magnitude of vector W, right, which is what I started to write, that would be -5 minus -2 squared plus -1 minus 3 quantity squared. So this equals, so -5 minus -2 is -5 plus 2. So this part inside of here would be -3, right? And this would, of course, be -4. So we would have the square root of -3 squared plus -4 squared, which equals the square root of, we get 9 plus 16 again, which is equal to the square root of 25, which of course is 5. Right? So in other words, the magnitude of V is equal to the magnitude of vector W. Right? They both equal 5. So what we're asked, though, in part B is, are V and W equal? Right? So I have some things just to write about this. So for vector V to equal vector W, vector V and W must have the same magnitude and direction. Right? So we know that the magnitude of V equals the magnitude of vector W, which both equals 5. So vector V and vector W have the same magnitude. Right? However, it is clear that they do not have the same direction. Right? It's clear because their directions are opposite. Therefore, vector V is not equal to vector W, right? So what I mean by their directions are opposite, right? If we look at this, vector V is pointing upward, right? Like to the, towards the top right, and vector W, the direction is going downward, like bottom left. So they're actually going opposite directions, right? It turns out that this line segment has the same slope as v, right? They'll have the same slope, but they're pointing in the opposite direction. So they can't be equal, right? They're not the same. Right? We'll actually talk about how to symbolize that when a vector is essentially just kind of pointing in the opposite direction, right? But has the same magnitude and really the same overall slope, right? So what I have now is just some more practice. So we're going to look at like how to visualize like adding vectors together and some things. And rather than just giving you a bunch of definitions, I wanted to give some examples to kind of talk through that, right? Because this section is, like I said, a lot of kind of definitions, if you will. Right? Some of you have maybe never used vectors before. So example 2, we're given this diagram of vector v and w, and we're asked to sketch v plus w by replacing an initial point of w at the terminal point of v, right? So I want to basically take w and kind of take this point and put it up here and redraw it that way, right? So this is referred to as the head to tail method, right, of adding two vectors together. So the way to think about it is, if this point comes up here to its head, then think about, how do I draw this vector, right? So I'm going to go downward 1, right? And then I'm going to go to the right 3 units, right? And that point would be where it ends, right? So then let me grab that ruler back, try to draw between these 2 points. I'm going to just get rid of those. So that is vector w, right? So then what you do to find the addition of the vector is the addition vector is going to have this same initial point, and the terminal point is going to be on the second vector, right? You go the head to tail. So you line the vectors up head to tail, and then you draw a line going from head to tail. Right, so this line is v plus vector w, right? So sometimes that's referred to as the resultant vector, right? Or sometimes people use an r to denote that vector. Right. So let's look at another method. So this is actually called the tail to tail method. So we're going to do the same thing, and you're going to find that this has the same overall result, right? Notice that this endpoint is at the point 6, 6, and this point is at 1, 3. Right, so just note that, and it's going to be the same for part B, right? We're just using a different method. So that how the tail-to-tail method works is I'm going to take this point, of the tail for W, and I'm going to put it on this tail, right? We line up their tails. Instead of going tail to head, we're going tail to tail. So same idea, right? I'm going to go down 1 unit, so I need to go down 1 unit, and then I go to the right 3 units, so I need to go to the right 3 units and draw a point, right? So that's how I get from, like one point to the next, if you will, from the initial point to the terminal point. So let me just erase that, and then I'll draw the vector in. So there's W. And then essentially what we do is we kind of turn this into a parallelogram. So I'm going to use a different color to do this. So look at vector V. We're going to go to the right 2 units, right? So to the right 2 units. And then 1, 2, 3, 4 up. So 1, 2, 3, 4 up. we're going to have a point here. Right, so I'm just trying to draw vector v in here, and I'm using a different color. And then we connect their tails, and that is going to be vector w. And then lastly, I'll use a different color for this. Lastly, you're going to connect where the tails and the heads meet. Right, so you're drawing like this diagonal in. Right, so that result, that's the resultant, right? Or vector v plus vector w. Right. So notice this point is at 1, 3. And this point, so the initial point's at 1, 3. The terminal point is at 6, 6. Right? Which is the same as what we had up here. Right? All right, so this one, we want to sketch v minus w by replacing the initial point of negative w at the terminal point of v. So we're going to do the head to tail method again. Right, so just something to write out is vector v minus vector w is the same thing as vector v plus negative 1 times vector w, right? And it turns out if you multiply a vector by negative 1, it keeps the same magnitude, but it makes it be like opposite direction, right? So this makes vector w be the opposite direction. Right. In other words, if we come back up to example 1, it's actually true that vector w is equal to negative vector v, and vector v is equal to negative vector w. Right. These are actually opposites of each other. Right. So they have the same magnitude, and they have the same slope. Right. But the difference is they're pointing in the opposite directions. Right. So in other words, if this is, let's say, vector x, then negative x would look like the same, like if you completed the line like this, right? And notice that they kind of form a straight line, right? So in other words, if I took this point and put it here, right, and move that over, it would line up to have the same slope, right? So when I draw vector w, notice I go to the right 3, so I'm going to go to the left 3. And then with vector w, I go down 1, so I'm actually going to go up 1. So this point and this point are going to form the vector. So this is vector negative w. Right? So we want to add those together. Right? So I just basically want to take this vector here and just pull it, take this point, this initial point, and put it up here. Right? So I'm going to go up 1 and to the right 1, 2, 3. And this is the spy land on. Right? So I'll just delete that, and then I just need to draw this in. So this is negative w, And then, since I'm doing the head to tail method, if I just draw a vector going from the head of the first one to the tail of the second one, then that vector will be vector v minus vector w, right? So now we want to do the same thing, sketch v minus w by drawing v and w with the same initial point, right? So I pulled this example out of the book, but I think there was a typo in the textbook. I think that this should have been negative w, right? But either way, we're just trying to do the tail-to-tail method. So remember, we already had drawn vector negative w, and so we go up one, right? So I'm going to start here. We go up one, and then we went to the right 3. Right, so we end up at the point negative 2, 4. Right, so I'll just delete that. And then if I draw, oops, just draw a line segment connecting those and draw an arrow for the direction. That's what we get. And then now what I need to do is draw in vector v. Right, so here's my initial point for vector v, and vector v goes up 1, 2, 3, 4 units. 4, and then to the right 2. So we end up here. Right. So then I can add in another vector w here to finish out my parallelogram. And then the resultant vector, right, goes from where the two tails meet to where the two heads meet. So we go from here to here. And that is v minus w, right? So we get the same vectors before, right? The same initial and terminal point. Right? Now the next one's a little different. I have negative v and 2w. I want to sketch both of those in standard position, right? So remember, just as a note, that standard position is when the initial point is at the origin. Right? So we know what negative v already is from the previous example. So now let's think about what happens if I take 2 times vector w. Right? So actually what's going to happen is the direction is the same for the vector, but it's actually going to be double the length. Right? So that seems pretty intuitive, right? If I take twice times vector w, I would think that I'm like doubling the magnitude. Right? So 2 times vector w is double the length of w. Right. I actually don't have enough room to draw this on this sheet, so I'm going to use the graph paper off to the side. And I think just to kind of speed this up a little bit, I'm not going to use maybe not use the ruler and just try to freehand this the best I can really quick. Right, so we want the initial point to be at the origin, right? So what we need to think about is kind of like the slope, if you will. So let me just draw V and W in standard position. So V would be, we go twice to the right, and then the vertical change is 4 units up. So there's the other point. And then connecting those two, we get that this is vector V. Right? So if I want to draw negative Vn, we just kind of do the opposite, right? So instead of going up 4, we're going to go down 4. So 1, 2, 3, 4. And then instead of going to the right 2, we're going to go to the left 2 and make a point. Right? And I didn't show an axis here, but everything's going up by 1 for my interval. Right? So this is negative V. Right? Which was one of the vectors we wanted to graph. The other vector that we want to graph is vector, 2W. So let me graph W in standard position. So we want the origin to be the initial point, and then we go down 1 and then to the right 3. So we get a point here. And then if I connect the dots, that is W. So then 2W, as I was saying, is like adding another W in, right? So like if I go down 1 unit and then to the right 3 more, that would give me another W, right? So this entire length, so if I basically get rid of this dot in between and just draw that, then that is 2W. Right? So what we were after was this vector in gray and the vector in green. Right? That's what we were asked to draw. So in part F, we're asked to draw 2V and negative 2W in standard position, right? So I'm just going to modify my drawing from up here, right? So we're trying to draw negative 2WN. Well, that's just going to be kind of like the flip of 2W, right? So we go to the right 1, 2, 3, 4, 5, 6 units. So I'm going to go to the left 6 units. 1, 2, 3, 4, 5, 6. And then, so I'm, here now. 1, 2, 3, 4, 5, 6. And then I went down 2 units. So I'm going to go up 2 units. So I get a point here. So then, this line between here and going this direction, this is negative 2W. Right? So we had drawn that. And then the other one we want to draw is, it's negative 2W and 2V, right? So what I need to do is add on another V. So I went to the right 2, and then up 4, I believe. 1, 2, 3, 4. So we get here, and then just draw another line in between. So there's another v. So then the whole thing is 2v, right? So if I get rid of this and just draw a line from here to here, then that's 2v. Right, so those two vectors in standard position. Right, so I'm just going to write C graph paper right up there. So in the objective 2, what we want to talk about next is how to represent vectors in component form. So this is another can be useful characteristic. So essentially what this is, right? So if I have this picture of this generic vector here, so this is, vector v, which is the same thing as vector pq, right, by this picture, then we can write this in what we call component form. So component form is kind of like these, I don't know what you like, braces, right? And what we write is you write the horizontal displacement, right? So in other words, what's the length from here to here, right? So that's a units, and then what's the vertical placement? So we're looking for this length, right? And that's b units, right? So a is the horizontal displacement, and b is the vertical displacement. Right? In other words, this is like the change in x and the change in y when you calculate like slope or the distance formula, right? And then, so this whole thing here, this is what we call the component form. Right? So then here I just took this nice box out of the textbook. So this is a component form of a vector. So if we have if we have a vector with initial point P and terminal point Q, then we can find vector PQ by doing the following, right? So as I was saying, this is like the change in x, and this is like the change in y, in like finding the slope or distance formula. So notice that these look very similar, right? So you're taking like the x coordinate from the second point minus the x coordinate from the first point, and then same for the y's, right? So it's just the way we can calculate that horizontal and vertical displacement, right? All right, so then the next part is just looking at a vector in standard position, right? So if I have a vector in standard position, we know that that's when the initial point is at the origin, right? So if that's true, then the terminal point of vector v is going to just be, the terminal point of vector v, which is denoted by a comma b in its component form. The terminal point is going to be the point a comma b, right? Since it is in standard position, right? So of course, if I draw like the right triangle in, then the distance between 0 and a is going to be a units, and then the distance between 0 and b is going to be b units, right? So that's why that's just the point a comma b, right? So that's a nice thing about having the vector in standard position. Right, so then example 3, we have suppose that a vector v has initial point -4, 5 and terminal point -1, 12. We want to find the component form of vector v, right? So the component form for vector v is going to be equal to, right, I'd want to take x2 minus x1, comma, y2 minus y1, right? Where this, of course, we know that x1 equals -4 and y1 equals 5, x2 equals -1 and y2 equals 12, right? So if we just plug those values in, we would get -1 minus -4, comma, 12 minus 5. So this equals, so -1 minus -4 is -1 plus 4, which is 3. And then 12 minus 5 is 7. Right, so vector v in component form is 3, 7. Right, so basically what that means, right, if I just kind of draw this really quick, let me just freehand this really quick. So let me let my x increase by 1 and my y's increase by 2 each time. Right? So if I plot the point at -4, 5, right, we get this point, and then -1, 12. Hang on, I gotta go up a little more. So there's 8, 10, 12. So we had -1, 12. So we get a point here. And if I connect these two, this is vector v, right? So basically what that component form is saying, that's helpful, is if I basically just take this vector, put this point here, like kind of just drag it over and shift it over, then it will it'll land at the point 3, 7, right? So if I draw 3, 7 in, which is here, then we get to the vector, right? So the component form tells me my change in x and my change in y, essentially, right? So the component form 3, 7, this tells me I go to the right 3, and this tells me I go up 7 units, right? That's how you get from the initial point to the terminal point, right? So that's why that can be helpful. And we're going to do some operations with vectors, and we're going to see why the component form is also really just kind of nice notationally to work through this. So then part B says if vector v is placed with initial point at -2, 4, what is the terminal point of v, right? So in other words, what we're saying is if I take this pink point and I move it to -2, -4, which will be here. If I move that vector here, where will the ending point be, right? So you remember, this is the components of the vector. So I'm going to go to the right 3 units. So I'm going to be, here, and then I'm going to go up 7. So there's 2, 4, 6, 7. So it'll be here. And then if I draw the line in, that terminal point is at the point 3, or excuse me, not 3, 1, 3. Right? That's what we're after, is this point here. So I can do this, more algebraically, if you will, instead of just doing it pictorially, by doing the following. So the terminal point is going to equal, so I can just take -2 plus 3, 7 plus -4, right? So notice I'm just adding, and really, if to be consistent, I could do this, just do -4 plus 7. So all I'm doing is adding the parts of the component form, right, to the initial point, right? Because that tells me what happens, right? This is my change in x. This is my change in y. So by doing that, I'm going to get the point 1, so -4 plus 7 is 3. Right, so that's my terminal point. Right. So then now I have so objective 3, we're going to perform some operations on vectors in component form. So first of all, we have this idea of equality of vectors, right? So remember, the equality of vectors happens when you have the same direction, the same magnitude, right? So if I have a vector v in the component form a1, b1, and vector w in the component form a2, b2, then vector v is equal to vector w if and only if a1 equals a2 and b1 equals b2, right? So their components in the component form have to be the same, right? And if and only if means it goes both directions, right? So if that's true, the right's true, and also if the right's true, the left's true, right? It goes both ways when we see if and only if, right? And then the next box here, we have some operation on vectors. So if I have those same vectors v and w, if I add them, I can just add their x and y components together. And then when I subtract vectors, I can just subtract their x and y vector components together. And then if I multiply by a scalar, right, so that's going to just change the magnitude, I can just multiply each the x and the y components times that scalar, right? So that's nice to know. So if I have vector r plus vector s, this would be equal to negative 3 comma 10 plus 12 comma negative 7. And using the operations of vectors above, right, remember what we're going to do is add their components together, right? So I take the x's and add those together, and then add the y's, right, to get that. And then I can simplify, and so the x component, negative 3 plus 12 is 9, and 10 minus 7 is 3. Right, so the resultant of adding vector r and vector s together is 9 comma 3. So the next one, we're taking s minus r. So vector s minus vector r is equal to the vector 12 comma negative 7 minus the vector negative 3 comma 10. So this is equal to 12 minus negative 3, right, for the x component, and then negative 7 minus 10 for the y component. So 12 minus negative 3, that's the same thing as 12 plus 3, that's 15. And then negative 7 minus 10 is negative 17. Right, so that's what we're after. Right, and then the next one, I have some examples with multiplying by a scalar. And I apologize, this s, you can change that in your notes. This should be b, vector b. Right, so I have vector a, which is 11, negative 7, and vector b, which is negative 4, negative 6. So we first want to find what 6a would be. So 6a is equal to 6 times a, which is the component form 11, negative 7. So remember, the property here is I take 6 times the x component and then 6 times the y component, and we get something like that. And then we can simplify. So 6 times 11 is 66, and 6 times negative 7 is negative 42. Right, so that is finalized. And then part B, we want to find negative 3 times vector A plus 10 times vector B, right? So we can find this pretty easily. So just substituting the vector form in for each vector. Right, and then we want to basically do like order of operations, right? We want to multiply before we add, right? So we would take negative 3 times 11, comma, negative 3 times negative 7, and then plus negative 4 times 10, comma, 10 times negative 6. So this gives me negative 33, comma, 21, plus, and then negative 4 times 10 is negative 40, and then 10 times negative 6 is negative 60. And then now I can finally add these. So this would be negative 33 plus negative 40, comma, 21 plus negative 60. So negative 33 plus negative 40 is negative 73. And then 21 plus negative 60 is minus 39. Right, so there's that answer. Right, so then I just want to finish out this video talking about some properties of vectors. Right, so if I have u, v, and w are vectors and c and d are scalars, and the following is true. Right, so this first one we have v plus w equals w plus v. Right, so this is like commutativity of addition. Right, so that holds true with vector addition. And then number 2 is this is similar to the associative property of addition, right, for real numbers. So we have if I group v plus w plus u, and then I'm changing the grouping, so grouping w and u on the right hand side, then that holds true. And then part 3 we have vector v plus vector 0, right? So the 0 vector is equal to the component 0, comma 0. Right, so you can see number 3, we essentially have an identity, an additive identity. And then number 4, this would be the addition property of 0. And so forth. Then we have some things here with scalars. So like number 5, this would be like some type of like distributive property. Actually number 6 as well. Number 7 would be commutativity. And then number 8 would be a multiplicative identity. And then number 9 and 10 would be like a 0 property of multiplication. Right, so you can see that a lot of these properties are coming up. Right, so something that's true in math that you want to get used to, especially if you keep studying math, is just because you learn one property, like for example with real numbers, doesn't mean that property is going to hold true for everything. Right, so like if you work with imaginary numbers or vectors or matrices or other types of things in math, that might not hold true. So just because real numbers are commutative, right, under multiplication, meaning that 3 times 2 is 2 times 3. It doesn't matter the order that you change it in. That's not always going to hold true for all different scenarios, different kinds of structures, right? So what I want to do now really quick, just to finish this video up, is just show you that property 1 is true. Right? I won't go through all 11 of these, but just to give you a hint that we can show that property 1 is true. And of course all of these do hold. So let me just prove this. So let vector v equal have the components a1, b1, and vector w have the components a2, b2. Let these be vectors with a1, b1, a2, b2 be within the real number system, right? So be real numbers. Then the following is true, right? So I'm just going to, this is called like a direct proof. I'm just going to start with the left-hand side that we want vector v plus vector w, right? And then I'm going to show that this is going to equal the right-hand side of property 1, right? Show that it's w plus v. So I can replace vector v with a1 comma b1, right, just in its component form, and then plus, and then a2 comma b2. So I'm just rewriting v and w in their component forms. So I'll write off to the side in green, so this is using substitution. So then this would equal a1 plus a2, comma b1 plus b2, And what holds that true is we're just doing vector addition, right, that we looked at before. And then what I can do is this would be the same thing as a2 plus a1, comma, b2 plus b1. And that holds true because a1, a2, b1, and b2 are real numbers, and real numbers are commutative, right? So this holds true because of the commutative property of addition for real numbers. Right, so then this would equal a2 comma b2 plus a1 comma b1, and that holds true because of vector addition. Right, it's kind of like doing it backwards, if you will. And then now this would equal w plus v, right? And that's just by substitution. Because a2 comma b2 is w and a1 comma b1 is v, right? So that holds true. So we can say, therefore, vector v plus vector w equals vector w plus vector v. All right, so there's a conclusionary statement. And then remember, when you do a formal math proof, right, we like to do like a filled in box to signify that we're done with the proof, right? Or some people do QED, which is a Latin phrase, right? All right, so we're finished with this this first part of this section. So I'll be making a video for the second part. Thanks.